Okay, so here we're going to be going over standard 0.3, which is on linear algebra. And here we're just going to talk about some basic matrix algebra, some stuff about eigenvalues, eigenvectors, and just some different operations that you can do to a matrix. So we're going to be doing problem 2, and it starts off by defining what the trace of a square matrix is. So the definition is the trace of n by n matrix A is defined as the sum of the entries along the main diagonal. And in class we mentioned two theorems, namely that the trace is the sum of the eigenvalues, and the determinant is the product of the eigenvalues. And both of these theorems are very useful. They one good use of these is just suppose you have some matrix and you're trying to find the eigenvalues and you have a lot of ones in the matrix. It's possible that just by knowing certain rules about determinants and things and knowing these two theorems that you can sometimes come to what the eigenvalues have to be without using much work. And they can also come up in other proofs and they just pop up a lot, so it's nice to know these. We're going to start off by proving these two results for the 2 by 2 case, and this is going to be parts A and B. And then C, we just show that both of these hold for a 3 by 3 matrix. And then at the end, I'm just going to mention just an extra proof that's not needed, but it uses a little more abstract algebra, but it proves the general n by n case. And this is a thing I did in my advanced linear class last year. I think the proof's really neat, so I just want to share it with you guys. Okay, so let's just jump into the first proof in part A, which actually also gives a proof for part B as well, but let's just jump into it. So prove that the trace gives the sum of the eigenvalues of a 2 by 2 matrix A. So we will prove this result by observing the characteristic polynomial of A. Note that the characteristic polynomial of a 2 by 2 matrix can be written as followed. The determinant of A minus lambda I is equal to lambda squared minus the trace of the matrix A times lambda plus the determinant. We know that A should have two eigenvalues up to multiplicity. This is just a basic fact from linear algebra. And up to multiplicity just means that we can have repeated eigenvalues. So this means that the characteristic polynomial is equal to the product lambda minus lambda 1 times lambda minus lambda 2. And we should also note that just the characteristic polynomial is a polynomial lambda, so you may not see any x's here, but that's perfectly fine. So by expanding this product and comparing it to the first equation, it follows that lambda squared minus lambda 1 plus lambda 2 quantity times lambda plus the product lambda 1 times lambda 2 is equal to the first equation. And now it follows immediately that lambda 1 plus lambda 2 has to be the trace of the matrix, and that lambda 1 times lambda 2 has to be the determinant of the matrix. So this actually proves both results, but I'm going to offer an additional proof for part B because it's kind of nice, and it's the original way I did it. So prove that the determinant gives the product of eigenvalues of a 2 by 2 matrix A. So we'll prove this result by once again observing the characteristic polynomial. And we know this equation follows from above. And if we now set lambda equal to 0, on the left side, the lambda I becomes a 0 matrix, so we're just left with the determinant of A. And on the right side, the two lambdas go away and the negatives become a positive. And this gives us that the determinant is equal to lambda 1 times lambda 2. So this gives us another proof. So let's just apply this to a 3 by 3 matrix. And here we have a matrix A equal to 1, 0, 1, 0, 1, 0, and negative 1, 0, 1. We'll start by finding the eigenvalues of A by using the characteristic polynomial. So here we just have this, and then where it's equal to, and here I just shorten a little bit of the work, but it follows that by calculating the determinant of this, we get 1 minus lambda cubed plus 1 minus lambda. And here we can factor out a 1 minus lambda and group this. And we'll have that it's equal to 1 minus lambda quantity times 1 minus lambda squared plus 1, all in parentheses. And here we can just factor this out and we get this nice thing here. So if we set this equal to 0, we can find our eigenvalues. And it follows that if we factor this, we have the eigenvalues 1 plus or minus 1 plus I. So now it remains to show or find the determinant is equal to the product of the eigenvalues and the trace is the sum of the eigenvalues. So for the determinant, we have the determinant of A. I'm not going to show all the work out again, but it's equal to 1 times 1 plus 1 times 1, which is 2. And that this is also equal to 1 minus I squared. And then we can just pull, this is a difference of squares, so we get both the 1 plus I and 1 minus I, and then there's just a factor of 1 here. So this gives us that the determinant is equal to the product of our three eigenvalues. And similarly, we can look at the trace, and the trace is equal to 3 because we just have 1 plus 1 plus 1. And then this is also equal to 1 plus 1 plus I plus 1 minus I. The i's go away. So, therefore, matrix A satisfies the two theorems from above. So, the last thing I'm going to mention is just talking about the general n by n case. And this uses something with a matrix which is called the Jordan canonical form. And this is just a way that, so not all matrices can be diagonalized. That's the thing that you learn in linear algebra. But every matrix does have a Jordan canonical form. And it follows that this form is always upper triangular. And so the main diagonal is just going to have the eigenvalues of that new matrix is just going to be the three things on the diagonal because it's, so just I guess the n things on the diagonal. And then, so it follows to show that these two matrices are similar, which follows just because all Jordan canonical form matrices are similar to their original matrix. And it follows that similar matrices have the same eigenvalues. So this is just a really cool proof. I thought I'd mention it. So this proves it for the n by n case. And similarly, the trace argument holds in the same fashion. So thank you, and that's it.